I'm not verified. I don't know why.
Yeah.
I'll probably be in the Caymans. Trying to find a stuff.
I gotta get over there.
Who is ready to submit homeworks? Whose homework is ready?
No.
Okay. Alex?
Sure.
It can look a lot better on Friday.
But you have something.
I have some.
Anyone else want to show how bright he or she is?
I'm
Okay, so these two get extra credit, but deadline is postponed to Friday. So we will probably you have like in the middle of completing, but the goal is not to torture minds and reduce grades, but opposite. Please approve and make sure that everyone completes it like 100% or a little higher. Evening session will partially be on homework, mostly on your questions. I will not be like giving too much instructions. Main goal for evening session is new code that we will be practicing almost until the end of the semester. So it is a longer code, and you will be modifying and utilizing it. And in about a couple of weeks from now, you will tell each other how it works. So let's let me distribute something. If you do not remember which homework you are doing, I finally printed it, so it's a little too late, but just in case. Alex claims that he completed it, but now you know what you have to do. And another thing. So we are starting, today is a special day, we are starting a new chapter in the lecture material, and we are starting a new chapter in lab material. So one copy is for your memories and pleasures, and there will be one more copy with a little symbol. I didn't bring you anything. I do. Okay. So on the copy with symbol, please leave your autograms near the subject that looks reasonable to present. So it's a couple of dozen subjects, and we need to split it evenly between, well, formally it's like 11 registered, but right now I count a little less. Any questions, suggestions right now? No, good, thanks. I think I need to be running forward like crazy because we have double the amount of material. So goal, we will have two things. One leftovers from previous lecture and then new chapter. From previous lecture, we will complete conversion of time-dependent Schroedinger equation into matrix form. We are tired, at least Ben is tired of derivatives and wave functions that continuously depend on position. So we want to keep track of the same physics and chemistry, but get rid of wave functions. If you ever need to get rid of wave functions, you yes.
Are we signing up for like one line or like the whole section?
Number of sections is a little less than number of people, so select a couple of lines. Ideally, lines following each other. It will be easier for me to. But if you really hate one subject and like another one, you can toss. So, when you need to get rid of wave functions, what do you do? Do not tell me just forget and leave the class. What do you, if you still want to have some equations, but you need to get rid of the wave function?
Conjugate?
Yes, and integrate. Right? To do the same operation as we do for normalization. And I know you hate scrolling back through your memories, but once upon a time we went through Heisenberg equation of motion, which is, by the way, part of the homework, where we transferred consideration, focus from wave function to expectation value by putting bra and cat from beginning and the end of the operator. And then we have matrix elements rather than wave functions. So multiplying wave function by its conjugate eliminates wave function and eliminates basis function if we expand the function in some basis. Well, enough talking. I'm going to jump, or maybe too optimistic, run through the slides. So, instead of wave functions, if we are looking to some to find results of measurements, we are transferring to matrix elements. So we multiply operator by wave function and integrate from left and right by what? Bra and okay, and then instead of differential operator and wave functions, we have just set of numbers in matrix form. In case we need to find the expectation value of observable, we can replace our previous protocol with taking these matrix elements, multiplying by row and column list of expansion coefficients. So it is equivalent. You get the same expression for expectation value. So matrix element times product of expansion coefficients. If you remember what was on previous slide, which you technically could, it was the same expression, but before it was obtained as a convolution of bra and cat wave function with differential operator. Now it is convolution of the row and column vectors of expansion coefficients with matrix of matrix elements. Good?
Will that give a 1-by-1 matrix at the end?
What do you mean 1-by-1 matrix?
So if you multiplied all those out, that would give a 1-by-1 matrix.
Which is called like a number, a scalar. Right? Expectation value is typically a scalar.
Okay.
Unless you are working with like 3-dimensional things.
Okay.
Sometimes it is comfortable to use concept of density matrix, which is a product of this expansion coefficients, and it is stored as a matrix. There is a math operator, so-called trace, when you have a matrix and you just add together diagonal elements. There is a way to express expectation value of an operator by multiplying density metrics which specify state of a system at a given instant of time by matrix elements of the observable that we need and taking trace. So if one does this little exercise, row by column, repeat it again and again, and then adds together diagonal elements, then one will get row 1, 1, J 1, 1, row 1, 2, A 2, 1, row 2, 1, A 1, 2, row 2, A 2, 2. And if we recall that these row elements are just products of the expansion pairs of expansion coefficients, okay, we will get again the same expression for expectation value of the observable. In some circumstances, this approach can be more favorable and can work a little better than wave function. And state of the system can be specified either by column vector of expansion coefficients or by matrix of this pairs. Okay. We will not use it very often, which is safe, but better with more bird's view. So you will see there is trace of density operator times operator that we want to find. Okay, according to Gage, the way to get rid of wave function is to multiply it by conjugate. So here are basis functions, eigenstates. We use very often eigenstates for a given problem are used as basis set. This is probably the most important saying, and I missed it last time. So we use solution of time independent Schrödinger equation, set of solutions, set of wave functions as basis set. We expand any function in this basis. So orthogonality is the way to convert wave functions into numbers, zeros or one. But if you have the actual wave function which is in a superposition, then this basis function is multiplied by exponential coefficients. We may get rid of the basis functions, but the coefficients will still stay in our consideration. So we are going to do some steps. The step is to plug the superpositional state, which is adding together several basis functions with expansion coefficients into time-dependent Schrödinger equation into the, and then look what will be going on. Then, after plugging in, do not click here. I have something much better to type. After plugging this equation into there, we will practice the idea of Gauge. We will multiply everything by conjugate wave function and practice elimination of wave functions. The crossed hat means that it is KET, not CET. So this is most loaded and most complicated slide for today. So after we plug in the superpositional state expansion over the basis into Schrödinger equation, time-dependent Schrödinger equation, we have derivative on the left, and Hamiltonian multiplies this stuff on the right. Our goal is to eliminate wave functions. So we multiply everything by the conjugated wave function from the left. In order to have this notation shorter, we are using this broad notation. which means phi star, right? Conjugated. And when bra and het are sitting together, it means we add the integration. So first term, we have state number m, which means we do not specify which one. It can be arbitrary. It can be 1, 2, 3. And then expansion basis m, derivative expansion basis on the left. And on the right, you see the Hamiltonian that was acting on the basis and expansion coefficient is multiplied by this bra from left. And we already identified that matrix elements of Hamiltonian will pop up here and there. Okay? So we already do not have wave function on the right side. Instead of wave function, we do have only the matrix elements of Hamiltonian. The basis functions, which we have chosen as the functions that we have chosen as for our basis, are solutions of time-independent Schrödinger equation. Therefore, they are time-independent. So basis states do not depend on time. Therefore, our derivative will be applied only to the expansion coefficients, and we will not practice the product rule and take derivative of the this convolution or basis function, because they do not change in time. We are not done, but the hardest part is over. So if you have protests or questions.
You said the derivative only affects what?
Well, if I would be more rigorous and meticulous, I would move this angular brackets to the front of derivative. So this sign of derivative right now acts only on this C and doesn't act on this one. So what is left? We need to practice this convolution. Also, since we haven't specified what the value for m, which basis state m is, it implies that we practice the same equation for all possible numbers m. Right now, all possible, which will mean 1 and 2, because we do not have time and steam to do further. So we will rewrite this equation twice, for m equals 1 and for m equals 2. And then we will practice orthogonality, right? This means wave function number n multiplies by, conjugated by wave function number 1, integrated, right? Which will be 1 if m equals 1 and 0 if m is something. So we need to rewrite equation that we looked at the previous slide 2 times for m equals 1 and m equals 2. And we need to convert our convolutions into numbers. So if m equals 1, 1 and 1 will be 1, right? Because the indices are the same. So the orthogonality rule can be rewritten as m equals delta m, which will be 1 if m equals 10, 0 if m not equals 10. Right? So it's this is a notation for integral by m star by m dx. Right? So, which obeys the normalization. So when we see 1 and 1 bracket, it will be 1. When we see 1 and 2, it will be 0, because numbers are different. Here is 1, here is 1. Then if we compose the convolution of 2 and 1, it will be 0, right? And if you compose convolution of 2 and 2, it will be 1, just because the indices coincide. And then in the expression that I hope we can remember from last slide, there were derivatives of expansion coefficients time convolution. And here it was also derivative of second expansion coefficient. But the convolution here comes to be 0, so we cancel this term. And for the m equals 2, here it was the derivative of expansion coefficient 1 multiplied by convolution. But we found that it is 0, so the whole term is cancelled. So due to orthogonality relations, we parse only one expansion coefficient out of the longer list. Right? So this 1 and 2. And if you continue for larger, for next and next base set, it will be derivative of C3, derivative of C4. And here it will be very similar to this matrix elements times other expansion coefficients. Any protests or questions? Yes? No? Everyone is happy? So, no one shouts to me telling liar. It's good.
Just to be clear, when you have the 2 in front of the bra, it means the convolution or the wave function star of the wave function 2, right?
You mean this 2?
Yes.
It's not in front. It's I'm just writing m equals 2. This one is the same as 2 bra 1 cat, which means integral phi star 2 phi 1 dx.
The last part is what I was asking.
So we have got set of linear differential equations for unknown expansion coefficients C1 and C2, right? Here's differential equation for C1 that the derivative depends on C1 and C2, and here we have the differential equation for C2, which depends on C1 and C2. So those two equations are coupled, right? You cannot solve one and forget about another one. They need to be solved together. Where is matrix form of Schroedinger equation?
Is it on the right side?
Well, these two equations together, set of linear differential equations, can always be saved, stored, recorded in matrix form. So if we look on this expression, a bigger amplitude of motion because it is so big equation. So if we look here, it looks like practicing row by column. So first, if you have a matrix, so H11 times C1, H12 times C2, row by column, you can assume that there is a column vector of C1 and C2 at the right side of expression. And here it will be, again, row by column, but if this 1H1, 1H2, 2H1, 2H2 sets a matrix, and we can put this expansion coefficients out of bracket in a matrix sense. Do you see? Let me hope that it is already written here. Yes. So if we practice row by column, this row by this column, we will obtain the expression on the right side of the first equation. Okay? And it will be equal to the derivative of C1. If you practice row by column for the second element, we will obtain second equation that we had on previous slide. So as said, and also this is ugly. This is 1, 2, 3, 4, 5, 6, 7 symbols. So instead of 7 symbols, we can just write 3 symbols. 2, just remove the brackets. So we do have set of linear differential equations for unknown coefficient C that are stored in a form of column vector. And then this derivative of this column vector is equal to matrix of matrix elements of Hamiltonian multiplied by the column vector without derivatives. Make sense? I think it was the slide announced as the last one of the previous lecture. We're done. So we're done with previous lecture. And for practical calculations related to quantum problems in real life, in academic homeworks, maybe not always, but in real life, this is used much more often than continuous distribution. Because instead of continuous wave functions, we have just discrete coefficients, right? Which may evolve in time. Agree? And by the way, if the okay, I will scroll back. If the off-diagonal elements are equal to 0, then this equation will give the trivial accumulation of phase by the expansion coefficients. Like if our Hamiltonian coincides with original Hamiltonian that generated our basis functions, then there will be nothing interesting. It will be just boring phase accumulation. But most interesting phenomena, most interesting cases when one practices this equation is when off-diagonal elements are not 0. Okay, it's end of previous lecture. Please do not leave yet. So here are some notes for our today's lab. And we are starting a new chapter and new logical unit. So we are escalating in more systems. We already covered free space and one-dimensional box. And now we will deal with harmonic oscillator, where we will practice same style, same tools that we learned before. Time independent Schrödinger equation, the time dependent Schrödinger equation, Heisenberg, and there will be another concept as well. What is so harmonic in how are we studying the harmony in music, or where the word harmonic comes from?
A function that repeats itself.
Huh?
A function that repeats itself.
Good. Good. Any other? I'm fine with this. Okay, harmonic means good. Like pleasant for ears and eyes. So why, not why, I shouldn't start this question. Which physical object or chemical object did we start before? I know there was a free space in the box, but what was placed in the free space or in the box? Yes. Are you happy with dealing only with electrons as chemists? You also need like protons, ions, nuclei. Right? What is chemistry?
Studies.
Huh?
Studying matter.
And more detailed and narrow.
Study of how atoms arrange themselves.
Then it is just characterization of fixed molecules, but there are reactions, right? Dissociation, association. So there are groups of atoms that like each other so much that they stay close to each other. There are distances between atoms. And sometimes, if there is a reaction, they abruptly elongate, which means like dissociation, or some foreign atoms may suddenly find each other and set specific distance, which would be association reaction. Okay? So as chemists, you should be very excited about atoms changing distance between themselves, right? So atom A, atom B, and O is not atom, it is origin. B, and there is a vector. So what do atoms do if you drop the temperature below liquid helium to absolute zero?
Absolute zero.
Uh-huh.
They stop moving.
We will find in today, well, not in today, but in this chapter that they will perform zero oscillations still. It's one of the consequences of quantum theory. But if you forget about quantum theory and believe only in classical mechanics, yes, they will stop moving.
They have no net movement.
Yeah, yeah. So in average, they will stay at fixed positions with some oscillations around this center. So it can move a little forward, backward, right? But average distance between atoms stay. Why? Finally, I can ask a question. Logically. So why are they staying together?
Because of the attraction between their electrons and protons.
Okay, because they're so attractive. What does mean attraction?
Opposite charges like to
Oh,
stick around each other.
Urge to stay together.
urge to stay together. Yeah.
Urge to come together, I guess.
Yes, and if we are practicing scientific approach, so urge to stay together, it's like, attractive photograph. I need to find this person and stay together. But what does it mean? We have specific nomenclature of scientific words. Urge to stay.
Electronegativity.
More specific, more to the physics side. If two objects are urged to stay together,
I was going to say electromagnetism. That's not.
okay, it's strength of electric field, but I'm looking for words. You will
Charge.
charges more scientific words.
Force.
Yes. Yeah, force. So if they are far enough, there is an electrostatic force that brings them together. What happens if they try to be too close?
Force that pushes them away.
Yes. Yes. So attraction and repulsion that sets them at a specific equilibrium distance. What is better than force? Ease. what can replace force? Like if you logically and philosophically describe the same concepts, but we just want to avoid force.
Charge.
No, charge is the ability of an charged object to be affected by an object. But like if the object, if like a nuclei, feels more comfortable to stay at a given position and less comfortable to stay at another position. You know this idea. It's only semantics.
Energy?
Yes. Which energy? Energy
Free
can.
energy?
Huh?
Free energy?
It's too complicated. It's complicated. More basic. Which two basic forms of energy?
Potential kinetic.
Potential and kinetic. So which energy we are talking about?
Potential.
Yes. So potential energy is better than force because they are connected. Potential energy is derivative of force, and opposite force is derivative of potential energy. I will almost dissect.
You say force is the derivative of potential energy.
Yes. Is it surprising? If one place is more favorable for me than another one, it means difference of potential energy between these two spots, and the force will drive me to more favorable side. Okay, I do have generals 11 minutes for new subjects. So instead of scratching by finger on a blackboard, I just went to Wikipedia for word interatomic potential. So it is what you were telling about. If they are far, they do not feel anything. If they are approaching closer, there is a downhill incline that drives the atoms to be closer to each other. And when they are at the right equilibrium distance, the potential energy is minimum. Right? Like if you have some shape, like valleys and hills and billiard balls rolling there, they will find the lowest place. Right? And if we try to bring atoms closer to each other, the energy will start growing. Therefore, they will experience force in opposite direction. Force acts inwards if they far, and outwards if they too close. And this is equilibrium distance. Equilibrium distance. You can put it there. Position of atom A minus position of atom B absolute value. Right? So we can assume that our atoms are also quantum particles. They will have kinetic energy and potential energy. And they will move in the potential determined by this interatomic potential energy curve, right? So the Hamiltonian will be kinetic plus this potential energy, which will be good, correct, but not accessible for us at our level of development of mathematical muscles. We already know how to do no potential or infinitely high potential. And here, mathematically, it's a complicated curve. We need to start slowly but surely. And not only we, the whole humankind and people who are trying to practice quantum theory quickly realized that only few problems can be analyzed by pen and paper with rigorous math. Most of the problems are not possible to process by equation. They are processable only by numerical approaches. So we did just a little bit dive into real life, and we immediately realized, or I invite you to believe me, that it is real shapes of potentials like this will make life really, really hard if you try to derive some equations and solve for something, like find eigenstates or whatever. So we need to immediately declare that we are scared of this potential and design something simpler. Okay? Here's another one. We can focus. So it is a zoom in of the same potential. And if we are not interested in chemical reactions for a couple of weeks, by the end of the course we will, I hope. We are looking only at in the equilibrium, stable molecules, where, according to Ben, they keep net interatomic distance and can perform slight oscillations. So slight oscillations means very small elongations or contraction of interatomic distance in respect to equilibrium distance. Right? What will happen to the potential if we deviate from equilibrium by very small values? Just tell me what you see on the figure.
We'll try to go back to equilibrium.
Let's think mathematically, not no dynamics. Just if we manually increase interatomic distance and explore what will be the energy. Will it be smaller or bigger compared to
Bigger.
bigger? If you contract it, will it be smaller or bigger?
Bigger.
Bigger. So no matter whether we elongate or contract, potential energy increases. Suppose that we set off by a really small delta r to the left or to the right. How much will it get bigger? Where it will get bigger, when we go to the left or to the right? Well, looking on the figure, it will be a little bigger to the left, but if you look on it from the bird's eye, in a good sense, approximately the same. So which function grows if our argument changes to the left or to the right? Simplest function. When argument changes from positive to negative and function behaves symmetric, the same.
Next one.
Absolute value and
So like x squared.
x. Quadratic. Yes, quadratic. So if we write delta r squared, it will exactly reproduce this shape that will go higher if we deviate from equilibrium. Make sense? So now we may want to wrap up this idea in a more fancy and rigorous way. We discussed this last time. Taylor expansion, right? So if a function can be reproduced as a set of its equals value at point where we make expansion and then derivatives first, second, third times polynomial. Right? So it is a standard way to approximate complicated functions, especially in vicinity of special points. So why don't we practice Taylor expansion of the potential energy in the vicinity of equilibrium point? So we had this U of R prime potential energy that had some complicated shape. So if we believe Taylor expansion, and if we said that it was our R prime, then values of this potential energy in the vicinity of equilibrium will be actual value exact at equilibrium times first derivative at this point times elongation R prime minus R prime equilibrium plus second derivative of this one was taken near this point times square of this elongation, right? So what will be the first derivative of this function at this point? Let's scroll a little back if you do not answer immediately. What is the first derivative of a function? Geometrically, graphically.
I mean,
Slope. Yep. So what is the slope of this function near its minimum?
0.
0. So therefore first derivative is 0. So if we stop our Taylor expansion only in the first term, we will get nothing. We will start to believe that energy will be the same everywhere, which is not right. So if first term doesn't help, we need to go to the second. Then it will be second derivative times position minus equilibrium position squared. So we need to be masters of our scientific consideration. At least we need to be masters of the coordinate system. So why don't we shift our coordinate system in such way that system origin will coincide with the minimum. Then we can also drop the first term, right? And then we have only quadratic function, which means the potential for potential energy will be squared. Let's, I think I'm already over time, but it's better to, I'll borrow a minute or two. Suppose we already have the potential energy as square of the deviation from equilibrium. Then the force will be elasticity constant times elongation. So this R equals R prime minus R prime equilibrium. I just want to avoid the delta R notation. So if the force is this way, the potential is integral force, right? If the force is differential of potential, then it's opposite. So here is our potential. This K is elasticity constant, telling how strong the atoms will come back to equilibrium. And if we allow them to perform dynamics, to oscillate force and back, there will be frequency of their oscillations that depends on this elasticity constant and mass. So the heavier mass oscillates lower, lighter mass oscillates quicker. Right? So square root of elasticity divided by mass. And there are two frequencies, regular frequency and angular frequency. If we are just going to change notations to make them a little bit more comfortable, to go from force constant to frequency, which is more important. So if we take square and multiply by m, then elasticity constant is frequency squared times mass. And if we plug it into expression for potential energy, we have the energy as function of elongation or contraction of the one as mass for this ion that moves times squared frequency, angular frequency of this oscillations that it may perform, and it is related with infrared spectroscopy. On the infrared spectrum, you measure frequency at which atoms are moving. So you can directly measure it. And mass, it's just you look in the periodic table. And then elongation. If this is so, I'm almost done. Thank you for letting me blow a couple of minutes. So we always want to solve time-independent Schrodinger equation as a starting point. So Hamiltonian summation of kinetic and potential energy, kinetic energy is, as always, derivative over this variable, which is elongation, and potential energy is elongation squared, divided multiplied by this constant. So we plug it into here and have this equation. Right? So this is time-independent Schrodinger equation for harmonic oscillator, which describes quantum aspects of interatomic motion. This equation is much more complicated because it has this term proportional to r squared. If you're taking differential equations, you may realize that it is a little more challenging. So before analyzing practical aspects of interatomic motions, we will invest some time in solving this equation, which is a true mathematical challenge. Done? Here, if you want to enjoy it once again, and looking forward to see you 5 p.m. QVB 130.
This? Yeah. Wow. Oh, it. Big UPS checks. Mine is this.
It's good. It's good to know your priorities are.
Yeah.
See you guys later.
Oh.
Yeah, okay.
Good luck.
Thanks. See ya.
No one selected application of the code to harmonic oscillator. Okay.
Don't you know?
Is it right underneath it?
There's a few people.
I can say you So what?
How many?
Is that for